Thank you for watching Knowledge Academy. We start this topic. Let's talk about what is iterative integrals. Iterative integral is nothing but it's just a approximation technique we used on different kind of application. Okay. So let's suppose if I have a curve and I want to know this curve, area under the curve, I have one option I can take, I can take make a line here, make a line here, and find the exact volume inside this random shape. Okay, but many times we are not able to find an easy way to find this curve. Maybe this curve is easy this time, but if you have a shape like this, you know it's very hard to find all these boundaries and getting the area under those random curve or random surfaces, right? So what we do, we just try to make an approximation and try to slice this shape into different pieces. And number 1, number 2, number 3, number 4, number 5, number 6. And what we do, we just try to find the area under the curve of this particular shape, and then this particular shape, and then so forth and so on, and then add them together. Then we can add all the curve together and find the total area under the curve. On the other hand, if we have like a complete rectangle, right, it's easy. If I have an A, you have a B, I just say A times B, and I get the exact area. But here, the problem is that this is not a rectangle. It's a rectangle on 3 sides maybe, but on the 4th side, it just has some shape. So I have to make a line here. I have 2 options. And the option number 1 is I can make a line like this, 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 and I have this line. So I have 2 options. Number 1, I can make a line here and ignore this area and just take this line. That's my taken. And I can ignore this one. The other option is that I can go and then extend this area and then find this whole thing. So it means I have excessive area here. Okay. So one way or the other, what we do, we just try to minimize this approximation by making these slices smaller and smaller, right? And if we're making these slices smaller and smaller, we have to do more work. Okay. So that is the background of this. So let's talk about what is a double integral. The double integral in a uniform shape, what you can do, we try to integrate in 2 different axes at the same time. 2 different axes at the same time. Number 1, I can change the line, right? So I have a line like this, and I'm talking about the double integral now. And this is our main topic today. We're going to discuss. I have a line I can make from 1 to 2, right? So I can make a line here. I have to integrate this way, this axis. So basically this is my axis. So I want to call this is my x-axis. So I want to call this my dx, right? And then if I want to be iterate on this axis, I'm going to call dy, right? And if I have a function is giving, let's suppose if a function is giving in one of the axes, I probably can find the volume based on what is given. So the bottom line is that if line is given, I can find area by double integral, right? Dx and dy. But if I have an area is given, I probably can find volume, right? So what is given is very important thing. So what we can do, we just try to look into that. A simple example. So let's suppose I have a volume is given like this. Okay, this volume start here on this axis at 1. This maybe I can call it here. Dot 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 here. And 3. 1 and 3 along y-axis. So I'm going to say this guy is 1, means this point is 1 and this point is 3. Okay, and other point is 0 and 1. So if I go from x-axis, change the color. If I go from, so this is a y value, y equals to this, y equals to this. But if I go from this way, this line is x equals to 0 and this line x equals to 3. So if I want to write the integral here, I'm going to be writing here, and let's suppose a quantity is giving something. My first integral I'm going to be doing along x-axis. So x-axis, my limit is start with 0, I'll go to 1. Same thing if I want to do dy limit is start with 1 and 3. Okay. If I take the integral, I'm going to take the first integral first. So I'm going to say this, and it's going to be 2. So it's going to be x. I'm going to take with respect to x, and dy is outside. So I'm going to say x plus 2x squared y. And there is a limit 0, 1. So if I take the second integral, I'm going to substitute the limit to make it simplified. So it's going to be 1 plus 2y. Okay, and then I'm going to take the second integral with respect to y. So it's going to be just like that. And if I take it, it's going to be, y plus 2 divided by 2y squared. Y plus basically y squared. And the limit is 3, 1. If I solve this one, it's going to be look like 3 plus 3 square, and it's going to be 3 plus, and then I'm going to apply this one, and then minus the one limit is 1 square plus 3. So 1 plus 1 square. So it's going to be, this one is going to be 1 plus 1, 2, and then this one is going to be 9 plus 3 is 12 minus 2, the answer is 12. Okay. If you want to do this integral one way or the other, if you want to do this integral other way, you can do it. It's going to be doing the same thing. For example, if I want to write this one, this integral, like this way, 1 plus 4x1. Rather than dx and dy, I'm going to write in dy dx. I flip-flop these operators. So now the limit is going to be applied dy first. So dy is going to be 1, 3, and then x is going to be outside, so it's going to be 0, 1. If you solve it, it should get an answer to, 10. So it doesn't matter which way you solve. Okay. Let's take a look at another example in a different scenario. Now this time I have a volume. Determine the volume, bound the plane, which plane? The plane is giving z equals to 4x plus 2y over the rectangle. Over the rectangular region, and the region is given like this way, pretty much a range 0, 2 times 0, 4. Yep. So maybe the, just like that. There's maybe a plane is given. I don't know how this plane is going to be look like, but look like it's a pretty straightforward plane with x and y only z. So this is my z-axis, this is my y-axis, this is my x-axis. So maybe the plane look like this. Okay. In order to integrate the volume, so really what I want this area. So the volume like this, 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 this. So I want to add or calculate the volume under this cube. Okay. And this cube is coming here like this way. So in order to do that, I just want to get a patch on the top, maybe a little patch. And this is called dx, and this way I call, sorry, this one is dx, and this one call it dy. This one called dy. So what I want to writing my volume, first integral, second integral, and then I'm going to writing the my z. So z is 4x plus 2y. Now that I have a choice, which one I'm going to pick. So I can pick dx, dy. Okay. If I'm looking this rectangle, the one is given, it is starting with something and ending on something. So it's going to go for 0 to 2. So maybe this guy is 0, this guy is 2. So I just want to know that these are my limit. 0 to 2 is my x limit. Okay. And then 2 to 4 is my 0 to 2 my x limit, and 0 to 4 is my y limit. Okay. So this is my first limit and this is my second limit. So I'm going to say 0 to 2 my first limit and 0 to 4 my second limit. If I change this operator, I definitely have to change this limit. And this region, by the way, is given. This diagram is given. Right? And here it is mentioned here. This one is 2. This one is 0. This one is 0. And this one is 4. Okay. Now if I'm going to be taking the integral, so double integral, I'm going to take it. I'm going to take first integral for the inside one first, and the best way is doing it just like writing like this in a parenthesis, and then dy. Inside the parentheses, I'm going to be taking the integral, and it's going to be 2 dot x squared over 2 plus x y. And I just taking 2 outside, 1 2 is outside. So just to simplify this one, so 1 2 is I'm going to take the common and putting it outside, so it doesn't have to be into this. And just like here, you can take 2 2 common outside. So 1 2 stay inside, 1 2 is outside is a common. So 2y is inside. Y is basically considered as a constant. You're only taking integral for x. And here inside is 2, and 0 is my limit left. So I need to apply the limit before I take the second integral. So I'm going to say 2, 0 to 4, x squared plus xy to 0 dy is going to be 2 squared plus 2y minus 0 plus 0, and square. It's going to be pretty much look like this, and then dy. Make sure we do not forget that we have a limit 0 to 4 here. Since we have a limited space, we can erase this image. and then apply the simplify a little bit if we can before we take the second integral. 4 0, so it's going to be 2 plus 2, it's 4 plus 2y. Now I take the second integral, so 2, and just want to make sure this is our volume going on here. So it's going to be 2, and inside 4, okay, it's going to be 4y plus 2 over 2y squared, and then 4, 0 limit left, and then let's simplify something. So this is going to be cancelling 4 plus 4 squared minus 0, right? Everything will be 0 inside the second term, and it's going to be 2, 4 squared plus is 32, 4 times 4 is 16, 16 plus 16 is 32, and this is going to be 64. Okay, that is my volume. Let's take a look at another problem. In this problem, we have, I need to solve this. I have a double integral, and the first integral outside one going from 0 pi by 2, 0 to pi by 2, the other integral going from 0 to pi, and looks like it's some sort of iterative integral for a trigonometric function, just like the limit telling me. And what I'm going to do, I'm going to write that function, and the function is giving pretty much now trigonometric function. So first thing was, first I'm going to be doing, I'm going to be just the solution and writing this 0 to pi outside, and then take the parenthesis and writing like this, 2 cos y plus sine x then dy. Okay, let's solve this one so we can apply the inside one integral first. 0 to pi by 2, 2x cos y minus cos x, and then it's going to be pi, x equals to pi, and x equals to 0, and then dy outside. Okay, let's apply the values of the limits. So it's going to be 2 pi by 2, this is pi, so 2 pi cos y plus, minus pi, and then minus, this whole thing becomes 0 because the cos x becomes 0, and then minus cos 0. Okay, and then it's a dy. If I simplify it further, it's going to be 0 pi by 2, 2 pi cos y plus, so this one is minus 1 and then plus 1, so it's going to be minus 1, cos pi is minus 1, then minus minus plus 1, and then minus minus plus 1, so it's going to be 2 pretty much. So what I'm going to do, I'm going to just write 2. Then I'm going to be writing second integral. I'm going to take it. So let's take a second integral in this step. Since we have a space limitation, we're going to be writing 2 pi sine y plus 2y. And right now I'm taking the integral with respect to y. Y equals to 0, y equals to pi by 2. Okay. Here if I substitute the value, it's going to be 2 pi sine pi by 2 is 1, sine 90 is 1, plus 2 divided by 2, so there's going to be cancelling, so only pi left. Minus, if you substitute this over here, sine 0 is 0, so everything becomes 0, and 2y, 2 means 2 times 0 is going to be 0 everything. So on the second term, everything will be nullified, only first term left, so it's going to be 2 pi plus pi, it's going to be 2 pi plus pi, the answer is 3 pi. Okay. Just for testing purpose, maybe you can take this value, right? You take this value, and what you do, you just, for testing, you just writing like this, and writing the same function, and writing dy or dx, and then flip-flop the values, so the y value is 0 to pi by 2. Oops. 0 to pi by 2, and then this is going to be pi, and then 0. If you solve it, the answer should be coming this 3 pi. It is not coming, probably look like we have some mistakes going on, so make sure that we are not making any mistake. Let's do another example of this double integral. We understand what is a double integral, what their implications are. Let's take a look on another example. Okay. Before that, I'm going to be remind you one more thing. I think we already talked about that in a few minutes ago. It says method of iterative multiple integral. And what is a theorem? This is basically a theorem. And the theorem is, if I have a function fxy dx dy, you're going to be writing a, b, c, d. And now, if I want to take the integral, it's going to be c, d. We already talked about these things, so now it's making much more sense that we just try to rewrite what we just learned in a theorem form. So in your book, this theorem is given just like that. Okay. Same thing. Similarly, if I change the limit c, d, same function, dy, dx, you can see here, I try to bring this guy here, and then flip-flop these limits. Okay, that's what should be equal to ab, and then we take the integral for the internal integral first before we touch the outer one. So it's like a shell. Okay, you remove the one layer and then reach out to the other layer and then reach out to the other layer. That's how it works. You cannot reach out to the other layer before you remove the first one. So initially you have to start from inside and solving the inside one and then do it. So this is a theorem given in your book. Pretty much this is what we did a few minutes ago. I don't want to show you this in the beginning, so you will be surprised and scared from this double integral, but it's nothing but it's just We are taking double integral twice, just like the way we used to take single integral. Okay, let's do another example.
Let's take a look at another problem.
I have a function is given. I need to solve this, by the way, and the dy operator first, and dx is outside. So I want to apply the dy limit. Dy limit is 1 to 2, and the dx limit is 0 to 3. Okay. So what I want to follow the theorem again and just make sure I write what discipline says. Make these curly big brackets, square bracket, and inside I'm going to be writing my first integral. If you're not doing this step, you might have a chance that you messed up with the term. So make sure we write it this way, and then keep focusing on the inside parentheses first before touching the outside one. Okay, let's take the integral. So 0 to 3. I'm going to write the parentheses again. And after I'm taking the integral, so it's going to be taking with respect to dy. It means inside one, x is considered as constant, right? Because I'm taking the integral with respect to y, so x considered as a constant. So integral will be x squared as is, and there is only one operator y plus 6 over 2y squared. Okay, so I can write this one is a little bit simpler way. I can just take 3y squared minus x 3, and then y squared is going to be y cubed over 3. So this guy is cancelling out. I can write xy cubed with minus sign. Okay, and we need to delete this one too. So xy cubed and then dx. And I have a limit 0 to 2. Let's apply the limit so we can move forward with this one. And I apply the limit is going to be 0 to 3 outside one, which is not being solved yet. And 2 is going to go this one, so 2x squared plus 2 is going to go here. 2 times 2 is going to be 4 times 3 is going to be 12. And 2 times 2 times 2 is going to be 8x. Okay. Then minus, I'm going to apply the 0. So this term is 0, this term is 0. This term, the first term, y is 0. So it's going to be 2. I think I'm going to be here. Hold on. This one should be 1. Because I have 1 here. And this one's 1, 2. Okay. So I don't want to be nullified. All the values is going to be 1 y squared, right? So my edge is going to be x squared plus 3, and 1 times square is going to be 1 minus x, and then dx. Okay, let's simplify this term if we can. There's a lot of opportunity to simplify. So 2x squared minus 2x. 2x squared minus x squared is going to be x squared. Then 7x, 8x minus 8x, and then plus x is going to be 7x with minus sign. Then plus 12 minus 3 be 9. Okay. And now let's taking the integral for the inside one. So I'm going to erase this parenthesis, just apply the directly integral. We have a limited space. So I'm going to apply here is 1 over 3 x cubed minus 7 over 2 x squared plus 9x 3 0. Okay, and now substitute the values. And the last one is going to x, and everything is 0, so I think it's substituting the 0. It's going to be 3 minus c is going to be 9, and this 2 is not really doing anything, so 7 times 9 is going to be 63 divided by 2 with minus sign, then plus 27. If I take the least common multiplier or LCM, so 2 is going to be 18 minus 63 minus plus 84. Okay, if I solve, it's going to be 18 is going to be 370 divided by 2, so it's going to be 9 divided by 2. Okay, and that is my answer.
Let's take a look another problem.
Okay, let's continue this topic and do some more problem. Before that, let me just talk about this. We can also write the theorem of iterative integral is if you have integral like this, then I can write R T A. When I say R is my region, or write my range, and I can write this iterative integral. If I expand them, it's going to be expansion like this to integral, and I'm going to be writing R here in the operator dA. It could be anything. So that is my area. Let's suppose I'm trying to be doing this is dx and dy. I can do dx first and dy later, or dy first and dx later. So I can write like this. I also write other way if I want to calculate this arrangement, and we can call this is a double integral for an area of a region. Okay, so look some example. And I have a question. Need to solve this. And what do I have to solve is I have to solve this integral. But in order to solve this one, before I do anything, I need the range. So sometimes these questions is given in the form of these range are not given. They given in the form of question. So they may be saying what is the range, or how the area under the curve is going to be calculated for this range. And the range is given in the form of more like a syntax. If it's given in the iterative form, it's much easier if I just wrote like this and we solve it. But sometimes it's not given. Maybe it's given in this form. So 1 and it's go up to 6. So x is going from 1 to 6. It means it's including 1 and 6. That is what we have, 1 here and 6 here. And the y value starting with 2 to 5. So we are including this 2 and 5. But let's suppose if they're removing one of these equal sign, then you are forced to start with 3. And this one starts to 2. Depends on which way it's given. So in this curve, now in this problem, we don't have any area is given. So what we can do, we maybe can write any region like this. We can draw the region. And what we're trying to learn before we solve this problem, just to draw graphical representation. So right now what I'm doing is a graphical representation of a double integral. Remember I just mentioned to you sometimes the problem of double integral comes like they are right now. Sometimes they give you this form and sometimes they give you a graphical representation. So graphical representation is an easy way to understand how this theorem works. Okay. The first thing what I'm going to do, I'm going to be writing to solve. I'm going to be solving this in the form of my first, the way I'm writing here. So if it's a dx first, I'm going to start making. So this is my y, so I'm going to say this is my y axis and this is my x axis. When I solving with dx, my y is constant. So y is constant means the line should be like this. And I call this is a line method. And when I say line method is basically a generic name, I just give it to it. But the point is that what you're going to do, you draw the region, and then whatever derivative you're taking, make sure you draw the line constant. So y constant line is this is a y constant. I'm going to say y equals to constant. Because remember, sometimes the graph looks like this. If the region is complicated like this, then you have a challenge to putting what limit you're going to be putting. So if you have two integral and using dx, it means here means y is constant, right? So when you say y is constant, you're going to be cutting maybe line like this, and that is your limit, and that is your limit. Okay. When you do dy, it's going to be doing this one. Dx is going to be doing this one. Dy is the other way around. Let's talk about the dx first. Okay. Where is this thing? This is a very simple example to understand the graphical method or graphical representation. So what I'm going to do, I'm going to say is this axis go to 0 to 1 for x. So really it means x equals to 1 and x equals to 6. Here, this thing, y equals to 2 and y equals to 5. Okay, this is how it's given. When I'm going to solving with an outside, solve for, I'm going to say solve this one is I'm going to say solve for dy. So when I say solve for dy, it's going to be look like this pretty much. But you're going to be making a line like this because when you solve for dy, x should be constant. Here x is a constant and this is x value, so x equals to 1, x equals to 6. And here in this line, my x is constant. Okay, and these are the two limits, this limit and this limit. Here are the two limits, this limit and this limit. Okay. So let's solve this one and see how does it go. So I'm going to be writing 2, 5, and dx dy. If I solve further, it's going to be 2, 5, 6 minus 1 dy. It's going to be 5. So really it's going to be 5. And then I'm going to take the integral for 5. So it's going to be 5y. The two limits are 5, and then 2. So 5 times 5 is going to be 25. 25 minus 2 times 5 is going to be, so 25 minus 10 is going to be 15. So let me write 15 and that is my answer. Let me solve this same integral in other way. So I can flip-flop these. So dy first, dx later. I'm going to check if I'm doing something which makes sense. 6, 1. Okay, I flip-flop the limit 2. So 0 to 2. 5 to 2 is going to go inside and 1 to 6 going outside. If I solve this one, so it's going to be y come as is. Okay, if I further simplify this one, apply the limit, it's going to be 5 minus 2. 5 minus 2 is 3. So it's going to be 3. And if I take the integral, it's going to be 3x, and then 2 limit is 6 and 1. If I solve this one, so 6 times 3 will be 18, minus 3 is 15. So 16, 18 minus 3. And the answer is 15, which is pretty similar to what I got earlier. Yeah. So it proved me that I can change the operator, whatever the differential element I'm using, dx or dy, it should give me similar answer. Yeah. Okay, now we're going to be talking about a little bit difficult example.
Let's take a look at another problem.
So the problem is I have to find the just a given here. We need to find the area under the region. I'm not saying area under the region, it should be better to say area under the region pretty much sounds like a volume. So area of the region, and what is the region? Region is given like this. Remember I told you the region could be given differently in the form of equation, in the form of the integral, in the form of the graph or picture. They give you the image, and based on that you have to solve it. So here is giving pretty much like the one we just did it, just a different values. Y is kind of a little bit tricky. So really, if you pay attention, it's just nothing but it's just x value is going from 0 to 4, y value is going from 0 to under root square root of x. Since the region is not giving, maybe I can understand this one is square root of this. So look like both starting with 0. So let me just draw this. Right, this is my x, this is my y. Both starting with 0, so I'm going to start with 0. Then x go to 4, so it looks like I'm going to go from here to 4. So x equals to 0, x equals to 4. Y equals to 0, but y is going to square root of 2, so it means value keep changing it based on square root. So when x equals to 2, this one is equals to 1.44, because what you're going to do, you take the 2 here from x value 2 and then substitute here is going to be a little bit less. So look like this value is going to be grow much differently than the others. So it's a parabolic shape pretty much. If you say this is a parabola equation and this is what the parabola. So really this equation, if you put here, this equation is given in the parabolic form. So this is equation y squared equal to x. This is the equation of this curve, which I'm just doubling up right now. Okay. And at you reach this point, y equals to square root of x. Actually, y is following the same trend. So I leave it here. Now I'm going to be numericalized and putting the iterative integral on this 1 to d by dx. We already learned you can change the position of these order is going to give you the same answer. So at this point I'm going to be putting over there dy over dx and solve it and see how does it go. Okay, dy is first. So dy is going from 0 to y equals to x, and x is going from 0 to 4. The reason I'm writing this x equals to 0 and y equals to 0 just to make sure for a first time we just simplify it a little bit. You don't have to write this way like x equals to 0, y equals to 0. Just writing 0 is enough. And I'm going to solve this first before I go to the dx. I'm writing like this. Okay, I'm splitting them a little bit gap, and I'm going to solve the out inside one first. 0 to 4 come as is, and this one is going to be y, and the limits are 0 to x and then dx. If I solve this one, so substituting square root of x minus 0 then dx. I can also write this like this way, dx. If I take the integral, it's going to be 0 to 4. Let me just take the integral. So it's going to be 1 divided by 1 over 2 plus 1. I'm going to take it on the other side. It's just going to look like 3 over 2. Go. 2 over 3. And then x, 3 over 2. The limit is 2 to 0. Let's substitute the limit and see what's happened. So 2 over 3. And then 4. 3 over 4. 3 over 2 minus 0. 3 over 2. So this is going to be 2 over 3. And then if you take it, it's going to be 8. If you solve it, it's going to be 16 over 3. Okay, you take the 2 square, like 2, 2, and 3 over 2 for this one. And this thing is cancelling out, so 2 to the power 3 and 2 to the power 3 equals to 8. That is how I put the 8. Okay, this is my answer. Let's solve this one in another way. I can solve this way. It's going to be y equals to 0, y equals to 2, and x equals to y squared and x equals to 4. In this one, so the first one I'm doing this method, I use lines. So in the second method, I'm going to be using solving the the dx and dy. Let's solve this one. In this method, I have a line like this first. In the second method, I have a line like this. And that's a tricky part. If I say here you see the limit is starting with 4, 0 to the first integral 0 to square root of x, and that is the cutting limit. And in this time you cut here, so your limit is going to go for x first in the denominator, and here your x equals to 4, which is on the upper limit. Okay, dy part is pretty simple. You just do it here other way around. So when x equals to 4, y equals to, like this line, when x equals to 4, this point, y equals to 4, which is equals to 2. That is what we put here. Okay, let me just solve this one. This is going to be 0 to 2 x and then y square 4dy. This one equal to 0 to 2, 4 minus y square dy. If I simplify it further, take the integral with respect to y is going to be 4y, so 4y minus 1 over 3 y cubed. Okay, let's substitute the value of the limit. It's going to be 8 minus 8 over 3 minus 0 24 3 minus 8 over 3. If I solve this one, it's gonna be 16 over 3. Okay, and this is pretty much the answer. We had it earlier here. So both gave me the same answer. Okay. Let's looking at that problem. Okay. Here the finding the area of the region. And the problem is giving here something look like this, just a picture. You know, the picture is given like this. Remember I told you I gave you one, initially I gave you just integral form, right, and you solve it. The second I gave you R form, like a written text, and you solve it. Now third one, part C, I'm gonna give you a graphical form. So we need to solve the graphical form of the double integral. So we have to decide it how we're gonna be solving this, okay? So it's gonna be tricky. But the graphical one is the easiest one because, you know, maybe everything is more drawn for us. And here, equation is given y equals to x. 1, 2, 3, 4. So it's gonna giving breaking into 4 pieces. So 1, 2, 3, 4. Same thing here is gonna giving 4, 3, 2, 1. So this is a curve is given. We need to find the area under this region. This is what we need to find out, the area. Yeah, I should call this thing R. Really no function is giving. So what I'm gonna do, I'm gonna be writing double integral, and I'm gonna be writing dy dx. It's my choice. I just decided dy dx. In y, I'm gonna be writing a line. When I say dy, this is my y-axis, this is my x-axis. So when I say dy x should be constant, so let me just draw some green line. Not really green. Draw the green line. Now this green line is cutting here and here, right? This green line when x equals to constant, and this green line cutting 2 points, that's what I need to be substitute here. So if I substitute here, it's cutting 0, and the other value of y is x, right? That's where it's cutting. So here values of this, what is that, x, Now I'm going to be just substitute the value. Now I'm going to be changing the color and using dx. When I change the dx, I want to be substituting dx. I'm going to make another line, right? And if I make this line, is going to go from 0 to 4, because remember, this line cannot be cut here. This line go up to the extreme. So the second line should be going when y equals to 0. So I have to move this purple line all the way down, the maximum location. Okay, so this purple line should be there. Or in other words, I'm saying here, the second purple line, they have two things apply here. X is constant. Now, if y is constant, in this line, y is constant. Because I'm solving the x, so y is constant. The second condition is that y should be equal to 0. That's the starting point. And y should be equal to the maximum on the other end. Or I say is more in one other word, the y value should be here as minimum to maximum in this line. So if I go to the x, y value should be minimum and maximum. So y equals to 0 here and y equals to 4 here. So first line uses the vertical line method, which is the green line. Second does not really matter because you're starting from 0 to go all the way. So basically this, let's put it this way, this green line, this, forget about the magenta line or purple line. I'll erase this guy. I just want to show to you this part. Okay, for simplicity, take a line. Maybe white line. Okay, and take this line. And really putting in this, and then what's happening, you pass this line here and then pass this line. So see, these 2 points are, when you putting over here, what's the value of y? 0. When you move it here, what's the value of y? Cutting on the top, 4. That's what you need to be putting here. So let's substitute the values and we can just here what you're going to do is substitute the values. X equals to 0 to x, and then another one 0 to y. Okay, now does that make sense? And now I'm going to substitute the values and solve the inner integral first. So it's going to be y x 0. So if I solve this one, it's going to be look like just x. If I solve this one, it's going to be half x squared 4 0. So 4 squared is going to be 16 divided by 2, 8 minus 0. So the answer is 8. Let's do another problem pretty much in the same regard. And in this problem, we have again another shape is given.
Let's take a look at another problem.
Shape it like this. And here it is giving 1, 2, 6, 3, 4, 5, 6. And here is giving is going all the way down. Here is 1, 2, 3. We need to calculate the area of this region, unfortunately here. It's a tricky one, and the line equation is given y equals to 6 minus 2x. Okay, I'm ready to apply what I know of. That is my x, that is my y, as per standard. Okay, I'm about to write the integral. I'm writing 1, 2, and this equals to area. I'm going to apply dy first, and then dx. When I say it's dy, so x should be constant, so line should be drawn like this maybe. And I'm going to move this white line. For when I do the dy, it's going to be like that. When I do the dx, I'm going to be moving from left to right and see what are the maximum values of x. Anyway, I'm going to start with dy. So dy is going to go from 2, right, in the upper end. So I'm going to make this line, so it's going to start with 2. So I'm going to write in 2. And the upper limit is, this line is cutting to y, 6 minus 2x. So it's going to be 6 minus 2x. When I move this line all the way down to the left or go to the right, when I go all the way down to the right, x values here is 4, 2, 0. Okay, 0 to 4. The best way you can do, you can take this value y equals to 6 minus 2x, substitute the value of 2 here. So when you substitute the value of 2, x equals to minus 4, no, minus 4, then 2. So x value, here value of x is equals to 6, 0. So if you substitute the value, not 2, it should be 6. The bottom one is easy. You're just starting with 0. Okay, and here the y is, and I'm going to substitute, so it's going to be 6 substituting here. So this becomes 0, x equals to 0. And then other region, it is my first. And then when you apply the other one, x equals to y equals to, the down side is going to be 0. When you substitute a 0, you're going to get the value of 2. Not should be 2, not 4. Okay, so let's solve this one. 0 to 2, then y, 6 minus 2x, 2, then dx. Then I'm going to substitute the value 6 minus 2x minus 2, pretty much. Substituting the values. And if I take the integral this time, it's going to be, this one is going to be 4. Before I do anything, I need to simplify a little bit. And yeah, 4 minus 2x. Let's take the integral. It's going to be 4x minus 2 over 2x squared, and then 0, 4 is my limits. Substitute the values. 4 substituting is going to be 16 minus 2. It's going to be 2, sorry. So it's going to be 8 minus 2 over 2, cancelling out, and then 2 to the power 4 and minus 0 everything. So it's going to be 8 minus 4. The answer is 4. Let's look at another problem. Same thing, we need to find area under the area of the curve. So area under the curve or area of the region is pretty much same thing. And this time graph is going like this. This is 1, this is 2. The equation of this curve is given y equals to 4 minus x squared. Look like it's a parabola pretty much. And that is going to be, here it's going to be 4, but we don't care about this one. 3, 2, right, is given. So what I want to do, I want to apply the same method. this time area equals to double integrals d by dx. When I say dy, I'm going to apply the line like this. X is constant, so x is crossing here is 0. So I'm going to substitute the 0. The upper limit is going to be touching with y, 4 minus x. Okay, and then dx. When I apply the dx like this way, right, I told you just take the line and go all the way down and go all the way up. So when I go all the way down, right, and the value of x is 0, and from this equation, if you substitute y equals to 0, let's suppose y equals to 0, so 4 minus x squared, and x equals to 4, and x equals to plus minus 2. Yeah, minus we don't ignore because minus is on the other side of the x, like here. I'm only interested in this region, so I'm going to say it's x equals to 2, and that is my limit. When you do the triple integral, we do the same thing. We have first we don't do any does not substitute any value equals to 0. Second one, we substitute y equals to 0. Third, we substitute both x and y equals to 0, and we get the value of c. So right now we're just substituting value of y equals to 0, so we can find the x unknown, which is we found 2 here. Okay, let's erase this and solve this problem. Here I'm going to be writing 0 to 2 and solving the inner parentheses. So it's going to be y 4 minus x squared 0 dx 4 minus x squared dx. Let's substitute this one. 4x minus x cubed over 3. Okay, and I'm just doing a drag to step, and the value should be no parentheses here, and it's going to be 4 and 0. Okay, from here we just substitute the value inside, so it's going to be 2 8 minus 15, so 8, yeah, there's going to be 16 or 3, and that is my answer. That is the area under the region.
Thank you for watching Knowledge Academy. Please subscribe my channel.